Let's start again. Right, so hello, welcome to this review of the WJEC Double Award Physics Higher Tier paper from 2019. The aim of this, just want to go through, talk through some bits on the mark scheme, talk through what bits mean, and how you would obtain as high a grade as possible on this paper. Way you're going to do this is I'm going to talk to you up there every now and again. Obviously I'll be looking down at right, but I'm going to try to address the camera, and then I've got another little camera down in front of me, sorry about the squeaking, that has got the other information. Let's just stack my keyboard up out the way. There we are, it's better. Okay, so in terms of this paper then, the front page, it's always worthwhile having a read through. Key thing here is you've got to answer all the questions, and question 3 is our QER question. Okay, page 2, quite important. Page 2 is the formula sheet, has pretty much all the equations that you will need. It also has our SI multipliers, which are also very handy on this. We'll leave that page to one side. Got a blank page, we can get rid of that. So page 1 has some information on it. I know in my classes don't tend to go through these explicitly, how these labels, because they're generally quite straightforward. A lot of the information's on there, read through it, and yeah, don't worry about them. They're on all new appliances. They basically just give an idea of its efficiency and how much energy it wastes or uses properly. So the information is there. We're going to need it, so don't discard it yet, but we'll keep it to one side. We've got our cost of our televisions. So use the information from the labels and tick 3 correct statements. It's going to be 1 mark for each one. Television 1 uses less energy per second than television 2. Now, energy per second is also called its power. Power is measured in watts. So we're looking at the 2 numbers in watts. 2 is 78, 1 is 32. So 1 does use less energy. The largest television always uses the most energy. Now, if we look at just TV 3, it has got the highest energy of all 4, and it is the largest TV. But if you compare television 2 and television 4, you'll see that 2 is bigger than 4 in terms of its size, but 4 uses more energy. So that's not correct. Purchase cost, well, we look at the purchase cost, and actually 3 is 1.5 that of 2, so that's wrong. More expensive televisions always use less energy. Well, 3 uses, in fact, the most energy, so that's not correct. Television 3 uses 40 more units per year. Units of electricity, also kilowatt hours. Yeah, 1.2. 212 take away 172 is 40. So that's correct. And televisions with the same energy rating don't always have the same power. So if we look at 1 and 3, both are A. 1 uses 32, 3 uses 155, so that's correct. So 1 mark for each of these boxes. Okay. It is claimed that power is proportional to screen size. Now, if they're proportional, what that means is that power and screen size will always be the same ratio. So let's have a look. So the screen size we're using 1 and 2. So the screen size for 1 is 69. Its power is 32. That gives us a ratio of 2.16. So that's TV 1. For TV 2, if we do exactly the same sum, 139 divided by 78 gives us 1.78. So not true. The marks here, it is 1 mark for getting each ratio correct. And 3rd mark is 1 mark for correct substitutions, 1 mark for then getting other stuff right, but you only get 3 marks if you've also got the conclusion. So 1 mark for each correct substitution, another mark for getting either ratio right, but you only get that 3rd mark if you've got your correct, you put that statement in. Use this equation. Time in hours is units used in kilowatt hours divided by power in kilowatts to see how many hours TV2 is on for. So TV2 has a number in kilowatts of 108. Now it's got a power in watts of 78. Now, but it wants it in kilowatts. So we need to put that into kilowatts. We do 78 divided by 1,000. That gives us an answer of 1,384.6 hours. Which is fine. You could round that to 1,400 hours. That would be acceptable. 1,380 hours would be acceptable. 1,385 hours. Any of those would be acceptable. Okay. Now, common mistake students made with this question was they did not put the 78 into watts. Into kilowatts. They left it in watts, and that would have given an answer of somewhere in the region of 1.4 hours. Common sense. 1.4 hours of TV a year. Film is probably longer than that. 2 or 3 episodes of most programs will be longer than that. So that should then ring alarm bells in your brain that you've done something wrong. In terms of the marks, it's 1 mark for that substitution, 1 mark for getting the right answer. So use an equation from page 2. First time we need page 2. To calculate the cost of using television 2 for 1 year. Okay, so it tells us we're using 108 units in a year. The equation we want is the one that says cost in it. Cost is units times cost per unit. So 108 times 16, which gives us 1728. But that's in pence. Because our cost per unit is in pence, that answer will be in pence. Let's just scroll that up so you can see it. We want it in pounds, so we divide by 100 and we get £17.28. Part 3. The expected lifespan of a TV is 10 years. Simon concludes that it will be more cost effective to buy and run TV2. Sarah says it'll be TV4. Okay, so variety of ways of doing this. Personally, for me, I would do it this way. So I would have a nice little table here: TV2, TV4. We would have purchase. We would have running for 10 years. Put a pound sign. And then we'd have a column for total. Like so, and we could have a look. So our purchase price for TV2 is £1,000. For TV4 is 800. Now the cost of running for 10 years, well, we said for 1 year for TV2 it's £17.28. So for 10 years it's going to be £172.80. For TV4, well, TV4, if we look back in our information, uses, where's TV4, 172 units a year at 16 pence times 10 years. So our TV4 is going to be £275.20 over the 10 years. Now our totals here are going to be 1172.80 and 1075.20. So you can see TV4 is about £100 less over 10 years. So Sarah is correct. Okay, the marks then. 1 mark for that one, 1 mark for that one, 1 mark for getting these two sums added up correctly, but you only get this 3rd mark if you've made the statement again about Sarah. Yeah, only get 3 marks if you've actually written your conclusion, so take care with that. Other than to save money, why should consumers be encouraged to choose appliances that use less energy? Well, we're going to use or need fewer power stations. If we're using less energy, we don't need to generate as much electricity, pardon me. So need fewer power stations, reducing CO2 emissions. 1 mark for each of those lines. 1 for saying fewer power stations, 1 for saying reducing CO2 emissions. Okay, so question 2. Complete the diagram below to show the wavefronts of shallow water. Okay, so deep water into shallow water. This wave is going to refract. It's going to refract because the water will travel slower in the shallow water than it does in the deep water. So what that means is, as the bottom of this wavefront hits our shallow water, it starts to go slower, dragging the wave with it. Now what that also does, if you notice, is it shortens my wavefront. So you need at least 2 wavefronts in the shallow water showing smaller wavelength and bent like that join up. So they've got to join up. 2 marks. You've only got 1 that's joint, you only get 1 mark. The waves must be going in the correct direction, so anywhere down towards this bottom corner. We need at least 2. There we go. The wave generator in the deep water produces 5 waves in 10 seconds. Use an equation from page 2. Let's find our page 2. Put it safe in this pile of paper. We get rid of the rest. Don't need any of these now. So, equation from page 2. So we have to do a measurement from the diagram to determine the speeds. Okay, so we want speed of wave. Wave speed is frequency times wavelength. So wave speed, frequency times wavelength. Now the frequency, if we have 5 waves in 10 seconds, our frequency is going to be how many waves per second. So we want to get this to 1 second. So 5 divided by 10, which is 0.5. And our wavelength we need to measure from the diagram. So we measure that from the diagram, and on mine, I'm getting that to be 1.2 centimeters. Now we want wave speed in meters per second, so in fact we need to convert our 1.2 centimeters into meters, 0.012. So we then multiply those 2 numbers and we get 0.006 meters per second. 3 marks. 1 for working out the frequency, 1 for multiplying the correct answer, and the other is for getting the right answer. Okay, state how the frequency, wavelength and wave speed compare in the frequency, wavelength, wave speed compare in deep and shallow water. Well, I could do this a couple of ways. I'm going to do this on here with a nice little table, deep, shallow. We're going to have frequency, wavelength, speed. See, you can see that. There we are, nice little table. You could use a ruler. I'm not going to need marks for any neatness, so this will do. So the frequency for both of these is going to be the same. Frequency doesn't change. We don't lose waves when we change from deep to shallow, so they've got to be the same. Now, in our deep water, this is going to be longer, this is going to be shorter. When our waves go from deep to shallow water, they shorten up because of this bending, causes them to shorten up. Faster in deep and slower in shallow water. Remember doing the practical, picking up the boxes, dropping them, getting the water wave. As there was more and more water, the waves travelled faster and faster. 3 marks, basically 1 for getting each of those lines right on that table. Question 3 then. Now question 3 is our QER question, our quality of extended response. So this is the density practical question. So there will be one question on this paper somewhere which refers to one of the specified practicals. This year they picked on density. Okay, so we need to describe how the density of a small pebble, not a regular shape. So we can't say about measuring the pebble. We've got to use a different method. Right, well, to measure density, that's going to be mass over volume. That equation is on page 2. So we need to think of a way of measuring the mass and a way of measuring the volume. Well, the mass is dead easy. We're going to use a balance of the dry pebble. First step, we're going to weigh it. We're going to put it on a balance, determine its mass using a balance. Then what we're going to do? Now, we're going to find its volume by using the water method. Now, take care of this. Explaining this can be a little bit tricky, but what we're going to do is we're going to place enough water, or some water, in a measuring cylinder. Leaving enough space for the pebble. So a couple that I've seen people said fill the measuring cylinder. You're not going to fill it because that implies you put it all the way up to the top of the measurements. No room for the pebble then. So place some water in a measuring cylinder, leaving enough space for the pebble. We need to record the volume of the water. We record that in centimeters cubed. Okay, what we're going to do then, place the pebble in the water. Record new volume. Place the pebble in the water, record new volume. So how do we work out the pebble's volume? Well, what we do is volume of pebble will equal water plus pebble volume minus water volume. Or you could have numbered these, so volume in step 3 minus volume in step 2. Now we've already said the equation, we can then plug or use mass plus volume, not plus, don't use plus because we're talking about maths, and volume in equation. Density equal units will be grams per centimeters cubed. So something like that. Now, with quality of my writing, I might have lost a mark, but I've got all the science down there. So remember, in terms of the marks, most of the stuff, you've got pretty much all of that, 5 to 6 marks. If from your answer you can complete the method without having to know anything about this, you get 5 to 6. 3 to 4 marks, there's some bits which are unclear. So if you've said fill the measuring cylinder, for example, you're in that 3 to 4 bracket. 1 to 2 mark, you've basically described how to make one of the measurements. So you might have said weigh the pebble. That's 1 to 2 mark. All right, so that's that question. Question 4. So we've got circuit diagram, we've got some results. Plot the data on the grid below, draw a suitable line. So 4 marks. So the 4 marks are going to be 1 axes, 2 for the points, 1 for your line. So we want temperature against resistance. So the temperatures, we start. Now, loads of people like to start in. You don't. Remember, this paper is this size for a reason. So almost without thinking, I know that each big box is going to be a nice number here. I'm going from 0 to 100, so chances are each box is 100. So 20, 40, 60, 80, 100. Going up the side though, want it in kiloohms, that's fine. This is in kiloohms, going from 0 to 12.4. Now, one thing you'll notice is down in this bottom corner, I've done both like this, 0, 0. You could have done the 1 coming off with a 0, that's fine. But you've just got to make sure that 0 and 0 are both plotted properly. So we've got 1, 2, 3, 4, 5, 6 boxes. We're going to go up in twos. 2, 4, 6, 8, 10, 12. Because we've got a little gap at the top, so we're fine. We can go up to 12 because we've got a gap to plot that 12.4. Okay, so we now plot our data. Only thing to be careful when you're plotting this is remember, because we're going up in 2, each of these boxes is 0.2, not 0.1. So where you've got 2.5 for 60, it's not halfway in between, it's a quarter of the way up. Okay, line of best fit. So the line is going to be a curve, it's not a straight line here, that is very much a curve. Remember, bottom right to top left if you're left-handed, to the opposite way around if you're right-handed. So what I'm going to do is have my paper like this, going to do some practice goes before I commit, like so. You need to make sure your line, now this line, let's have a look at it a bit closer, this line probably wouldn't get the mark, especially for this point here. You've got to be within one small box of each of these, and I am just over, I'm 1.5 small boxes. So I'm talking about this point here. I probably wouldn't have got the mark for the line there, that's too tall. So that's a 3 out of 4 graph. The points are correct, the axis is correct, that line is just too high. It's probably a little bit wispy and a bit thick as well, perhaps should have sharpened the pencil. Just take care with your lines. I like graph, I think this is a good way of doing graphs. Do your points in pen so they stand out. Do your line in pencil so you can rub that out when you need to make changes. Alright, describe the relationship between temperature and resistance. So to describe this relationship, go, if you want to, watch the graphs video on YouTube. I'm going to put a card up somewhere, wherever I am. I'll put a card up, just so that you can see what's going on. Not see what's going on. So you can go through these, revise these different relationships. So as temperature increases, our resistance is decreasing. So as temperature increases, resistance decreases. Now that's one mark. We've said about the general relation. The second one is always about the rate. The rate is, remember how steep this line is. That line's getting less steep. So at a decreasing rate, second mark. Okay, a resistor of resistance 5 kiloohms is now added to the original circuit in parallel with the thermistor, which is at a temperature of 30 degrees Celsius. The same 12 volt power supply is used. Use your graph and equations from page 2 to determine the total current. Okay, now a couple of ways you could go about this. Probably the most straightforward way is to remember, two things are in parallel, they will both have the same potential difference across them, or same voltage across them. So the equation that we're going to need is that current is voltage divided by resistance. So the way I'm going to do this, I'm going to go, right, well, the current through the 5K is going to be 12 divided by 5,000, which is 2.4 milliamps, or 2.4 times 10 to the minus 3. Now what I need to know is at 30 degrees Celsius what my resistance is. So the current through the thermistor is going to be 12 divided by 8,000. Why is it 8,000? Because at 30 my line goes through 8. Again, you need to make that clear on your graph, on your results, and that gives me a value of 1.5 milliamps, or 1.5 times 10 to minus 3. Then my total current is going to be these two added together, 2.4 plus 1.5, which is 3.9 milliamps. 3.9 milliamps. Now you could give the answer in amps and put a times 10 to the minus 3 in there. That's acceptable, 0.003 amps. But yeah, milliamps. The other way of doing this is you do resistor formula. So you would do 1 over R. So the other way you could have done this, let's just do this at the bottom of the page, is you could have gone, well, 1 over R is 1 over 5,000 plus 1 over 8,000. And then gone, well, R is going to therefore be 3,080. V equals IR. So I equals V over R, which is 12 divided by 3,080, which also gives you your 3.9 milliamps. Both of these would have worked. In terms of the marks then, it's 5 marks. So what are the 5 marks? Now if I've done it this way, it's 1 mark for writing down 8,000 anywhere on that page. Second mark is for getting my 2.4. My third mark is for getting 1.5. 1 mark for adding them together, and 1 mark for the right answer. Okay. Kim then suggests that the current through the resistor and the thermistor will decrease as the thermistor cools. Explain whether she is correct or not. Well, resistors, the temperature, definitely in this range, has no effect. So current, let's use the right color. Current through, resistor will not change. So that's 1 mark. Now, as the thermistor cools down, its resistance will increase. So thermistor resistance will decrease. Not decrease, sorry, will increase. As the current decreases, not like that. As the temperature decreases, the resistance of a thermistor increases. You can see that on the graph, see that in the table. So the thermistor resistance will increase. So current will decrease. So 1 mark for saying that, 1 mark is for increase, 1 mark for saying about the current. Now to get to the third mark, what you have to say is whether she's correct or not. And now here she's going to be partially correct. Okay, so in terms of the marks, let's just highlight them. 1 mark for that statement, 1 mark for that statement, 1 mark for that statement, but you need to get 3 marks, some sort of conclusion, whether she's right or not. Blank page, we'll get rid of that, get rid of that, get rid of that, and just on page 2. A combined heat and power station uses the waste heat energy from a power station to provide heating for local homes and businesses. This increases the efficiency of the energy transfers. Describe how electricity is produced in a fossil fuel power station. Okay, so there'll be another card coming up somewhere, wherever they come up, with our fossil fuel power station video that goes into this in more depth. But key things is we burn fuel to heat water. Key points here: burn and water to get that first mark. All right. Now we to make steam. We don't actually get any marks for saying to make steam. We then have steam turns turbine. Set third mark. Turbine drives generator, making electricity. Third mark. So you have 3 marks. Burn fuel to heat water. Steam turns turbine. Turbine turns generator. Okay, Sankey diagram. Now this question was an interesting question. It was horrible. When I spoke about a maths department, because this is what I'd call a double percentage question. You've got to find a percentage of a percentage, which caught a lot of people out. So we have a look at it. 75% of the input power to a power station is transferred as useful energy. Okay. 40% of the useful energy is transferred to the national grid. Now, Helen estimates that 20 megawatts is the input power. Determine if she's correct or not. So 40% of the useful energy. So if we think about a Sankey diagram, this is our useful, this is our wasted. Now we are told that these two together is 75% of our total energy. Now what a lot of people made the mistake was going, well fine, that splits 40% to this one and 35% to this one. No. This here is 40% of 75. So our 3.2 megawatts is 40% of 75%. Or, if we write this down, 40% of 75% is, if you work that out, 30%. If you find 40% of 75, you get 30. Okay, so we now know that 3.2 megawatt hours, is 30%. So 100% is going to be 10.7 megawatts. So the input power is actually 10.7. So not correct. Now in terms of the marks here, 1 for the 30%, 1 for realising, well 3.2 is 30%, 1 for the working out the 10.7, but again you only get this final mark if you've written she's not correct. There are a few different ways. Look in the mark scheme, you could have gone right, well 3.2, you could have gone right, well 40% of the useful power is 3.2, so how much is the useful power? And that way you'd have gone 8, and you've gone, well 8 is 75% of the input, and then work out the input, you still get 10.7. A few different ways to doing it. Have a look at the mark scheme for the other ways. Oops. Okay, part C. Another power station produces 1200 megawatts of electricity at 50 kilovolts. The voltage is increased to 400 kilovolts by a step-up transformer before being transmitted to the national grid. Use an equation from page 2 to calculate the current. So we've got power, we've got voltage. So we want power is current times voltage as our equation. We're assuming we're 100% efficient. That just means whatever power goes into our transformer must come out. Okay. So our power is 1200 megawatts. So 1200 megawatts. In terms of the current, which current do we want? We want the current in the wires of the grid. So in this question, we've actually got some superfluous information. We don't need the 50. The 50 is no use to us. We know the power. It's the same power, 1200 megawatts. And we know the voltage is 4000 volts. And we want the current. So the current is going to be 1200. Mega is millions, so times 10 to the 6. Divided by 400 times 10 to the 3 because it's kilo. And this current then is 3000 amps. In terms of the marks, 1 mark for rearranging this equation, 1 mark for the substitution, 1 mark for getting an answer of 3000. Okay, question 6. Okay, so satellites then. We've got some information about different satellites. We've got geosynchronous, geostationary. We want one similarity. Well, both of these take 24 hours to complete one orbit. The difference is, though, geostationary always stays in same point or position above Earth. Whereas our geosynchronous don't. They just come back once every 24 hours to the same point. In terms of the marks, 1 for that, 1 for that. So yeah, geostationary always stays, so as the Earth spins, it always stays above the same point. Whereas our geosynchronous, in a day, it always comes back to the same point, but not necessarily for the rest of the day, it might be anywhere. Which satellite's in a geostationary orbit? What they're hoping here is, you just said it takes 24 hours to complete an orbit, so it's got to be 3. Okay, signal is sent from base station to the satellite. It is received by another base station, time delay of 0.48 seconds. Calculate the distance the signal has travelled. So we've got a time, we want distance, we've got a speed. So we have speed is distance over time. And we want distance, so that's speed times time. So 3 times 10 to the 8 times 0.48 gives us a distance of 1.44 times 10 to the 8 meters. 3 marks here. 3 marks are 1 for the rearranging of the equation, 1 for the correct substitution, 1 for the correct answer. Use your answer in part 2 and the table is the table to calculate which base station. So the information we have in the table is that each path here is 36,000 kilometers or 36 million meters. So we want to know our 1.44 times 10 to the 8. We want to know how many lots of that is our path. So 36 times 10 to the 6. We do that sum, we get 4 paths. So 4 paths, so 1, 2, 3, 4 gets us to C. So the 2 marks in this question, 1 for getting 4, 1 for getting C. If you just put C and no workings, you don't get any marks, though, because you had a 33% chance of getting it right. They're not going to give you the marks, considering this is the last question on the higher tier paper. So hopefully you've been able to mark your own paper or gone through and been able to see where you got things right, got things wrong, if you sent it in for marking. But now what I want you to do is to do a review. So there we go, on your paper, on your email or work this week, you should have also received a link to a Microsoft Forms document. You'll get 2, there'll be a hiring foundation, you only need to do 1. And it will look something like this. In fact, it will look something like this because you'll be previewing it. Okay, so you'll put your name in, your physics teacher, and your email address. That just means it's easier for us to track. Let's go back to this one. To track who's handed it in, and I can pass information on. Then what I want you to do is for each question is to go through. So question 1A, what mark did you get out of 3? There are a few where they were 1 mark questions. I can't change it. I can only give you an option of 2. Can't just give you an option of 1 using this. So just click 1. If you didn't get anything on a question, leave it blank. Then the final thing I want you to do is 2 things that did well, 1 thing you'd improve next time. By filling this out, I can then add up your score and I will give you your grade if you'd have sat this paper last year. Hopefully that helped. Slowly building up different videos on the YouTube channel to go through this course. So have a look at them. There'll be a playlist of those videos coming up around me. And please subscribe for more content. Thanks for watching. Hopefully this has helped.